In a previous video, we looked at the presence of molecular polarity and its influence on the type of intermolecular forces present for a particular substance and the strength of those intermolecular forces. But there are other factors that can influence how strong those intermolecular forces are. In this video, we're going to look at the influence of molecular size or mass and shape on the intermolecular force strength. Let's start by looking at the influence of molecular size on intermolecular force strength. And we are going to use boiling point as a proxy for the strength of the intermolecular forces in our different substances. So in general, the higher the boiling point of your substance, the stronger the intermolecular forces present. It takes more energy to pull apart those molecules from the condensed state into the gas state, so they're held together more strongly. Now here I have a graph that shows the relationship between molar mass on the x-axis and your boiling point on the y-axis for 4 different alkanes. Now alkanes are substances that have carbon and hydrogen, and these are what we call straight chain alkanes because the carbons are just bound together in a chain, one linear chain. Okay, now the important thing to note here is that for each of these alkanes, there's only carbon and hydrogen present, and that indicates nonpolar molecules. So these are all nonpolar, and I've removed the influence of differences in polarity or the presence of electronegative atoms on the intermolecular force strength. Okay, so all nonpolar molecules, the major difference between these is their size. Butane at the top here has more carbons. Methane at the bottom has less carbons. And what we see is that the bigger the molecule, the higher the boiling point, the stronger the intermolecular forces. Now, why does this develop? Well, ultimately, the bigger the molecule, the more electrons you have. And what is responsible for those intermolecular force attractions ultimately are the opposite charges that are associated with electrons being able to move to one side and inducing an opposite charge in the neighboring molecule. And the more electrons you have to move, the more charge, the larger the charge that they can induce, and the stronger the intermolecular force you have. So in general, larger molecules have more electrons, which leads to increasing polarizability. Ultimately, what that means, you get stronger intermolecular force attractions because you develop larger electrostatic attractions between your negatives and your positives because there are more negatives involved in larger molecules. Okay. Now let's look at the influence of molecular shape on intermolecular force strength. Here I have 3 isomers of pentane. Isomers mean that they actually have the same molecular formula of C5H12. So 5 carbons and 12 hydrogens in each of these structures. That means they all have the same molar mass of 75.12 grams per mole. So this time, we've got the same number of electrons, the same molecular mass. The molecular size is not going to be the influence on any differences we see in intermolecular force strength. They're also all carbon and hydrogen based. There's nothing from that upper right-hand corner of the periodic table. So polarity is not going to influence any differences that we see in intermolecular force strength. Now my isomers, starting on the right-hand side, N-pentane is one long chain of carbon atoms, and it has the highest boiling point and the strongest intermolecular forces. So just to show you those 5 carbons, this is your more traditional your structural formula, where you can see those 5 carbons actually just in one long chain together. Working to the left, isopentane, we've taken one of those carbons off the chain and actually put it off to the side. It's called branching. So this is actually the more traditional structural formula where you can see that branching effect where I've got one long chain of 4 carbons this time and this one carbon off to the side. Okay, now that small reduction in the chain and the branching effect has lowered that boiling point to 27 degrees. So we've weakened the intermolecular forces. Neopentane, the farthest one to the left, actually has a more branched structure. We've taken one more of those carbons off that central chain and moved it off to the side. So now we've got one in the center, and it looks like we've got 4 coming off of it. It's the most branched structure we can have for a pentane, for one of the isomers of pentane. And we see that it has the lowest boiling point and the weakest intermolecular forces. Okay, now the differences in terms of the branching ultimately affect the surface area that interacts between molecules. So we can see that in N-pentane, that long flat chain of 5 carbons actually has a lot of surface area that can come into contact with the neighboring molecule. The more surface area, the stronger the intermolecular forces. We introduce branching into the molecule, and you have less surface area that can actually come into contact between the molecules. And we see that with isopentane and neopentane, where we have the most branching. Okay, so in general, molecules that are flat have more surface interaction than spherical ones. As a result, they develop stronger intermolecular forces. In summary, intermolecular electrostatic attractions exist between all molecules, but the strength of that attraction depends upon several factors. The molecule's polarity is a major factor determining the strength of intermolecular forces. In general, the more polar your molecule, the stronger the intermolecular forces that are present. But the size of the molecule can also influence the intermolecular force strength. We see this effect when polarity is not a factor. In other words, when we're comparing molecules that have roughly equivalent polarity. Then we can see that larger molecules generally have stronger intermolecular forces. And when polarity and size are roughly equivalent between molecules, we'll find that the shape of the molecule can influence the intermolecular force strength. In general, flatter or more linear molecules have stronger intermolecular forces because they have more surface area available for interactions between the molecules. All of these factors overlap in determining things like boiling point and intermolecular force strength. It is easiest to be able to make comparisons about intermolecular force strength when you can isolate the influence of one of these particular factors. Let's look at a few examples. Here I have 3 different structures. They're all hydrocarbon-based structures. We have 2-methylpropane, ethyl methyl ether, and acetone. And by hydrocarbon, I mean they're carbon-based with a hydrogen skeleton associated with them. So the carbon is the black, the hydrogen are the white. We want to determine between these 3 molecules which one we would expect to have the highest boiling point and which the lowest boiling point. What we're really asking with this type of comparison is which one should have the strongest intermolecular forces and which one should have the weakest. In order to answer this question, we have to look at those different factors and determine which one of these varies the most between the compounds. So I've already isolated for you the molecular size. I've given you the molecular formula for each of these molecules and calculated the molecular mass. And you can see that between methylpropane, ethyl methyl ether, and acetone, the molecular mass does not change all that much. It's between 58 to 60 grams per mole. These are also all relatively small molecules. We have a slightly longer chain with ethyl methyl ether, but that's about it. It's slightly longer. these factors of molecular size and molecular shape really don't change that much. But when I look at the structures, what I see that is significantly different between the molecules is the presence of oxygen. So the red sphere in these ball and stick diagrams always represents oxygen. And oxygen is, from that upper right-hand corner of the periodic table, it's a more electronegative atom, and its presence in a molecule indicates the possibility of molecular polarity. So in this particular comparison, molecular size, molecular shape are probably not the major factors influencing our intermolecular force strength. It is likely the position of that oxygen. So now, when I look at my molecules, I can make some predictions. First of all, I know that methylpropane, my 2-methylpropane, does not have oxygen at all. So this is going to be the nonpolar molecule because it's all carbon and hydrogen, which means it's going to have the weakest intermolecular forces. Between the other two molecules with the oxygen, I have to determine the position of that oxygen, whether it's going to develop a stronger dipole or not. Now in acetone, I simply have that one oxygen bound to one carbon. Okay, that is in comparison to ethyl methyl ether, where it's bound to 2 carbons. So oxygen only sharing with 1 carbon, it's likely going to be able to pull those shared electrons towards itself more strongly. And it's going to develop a stronger dipole. Ethyl methyl ether, because the oxygen has to split its shared electrons between those 2 carbons, it's a little bit more balanced out. And this, well, it's likely still to have a dipole. It's still going to pull those electrons more strongly towards it. It's likely going to be a weaker separation of charge. And so this is going to be a weaker dipole. What that suggests to me is that this, the stronger dipole, is going to have the strongest intermolecular forces. And now, when I look at the actual boiling points, I can see that it matches that prediction of intermolecular force strength. The highest boiling point is associated with acetone, my strongest intermolecular force. The lowest boiling point is associated with 2-methylpropane, my weakest intermolecular force. Let's look at one more example. Okay, now again, we're going to use boiling point. Ultimately, to determine our differences in boiling point, we're going to predict the differences in intermolecular force strength between these 3 structures. We have what's known as germane, which is germanium tetrahydride, GeH4, silane, which is silicon tetrahydride, SiH4, and methane, which is carbon tetrahydride, or CH4. Okay, now, I do see hydrogen present in each and every one of these, but what that hydrogen is bound to, well, it's not nitrogen, it's not oxygen, it's not fluorine. These are not any of the atoms that are in that upper right-hand corner of the periodic table. They're not very electronegative at all, which tells me that these are largely nonpolar molecules. I don't have any hydrogen bonding. Again, remember hydrogen bonding, you have to have that hydrogen directly bound to nitrogen, oxygen, or fluorine. It's not just that hydrogen is present, okay? So, no nitrogen, oxygen, or fluorine, no hydrogen bonding. We're probably not looking at a difference in polarity here. That's not the strongest difference we're going to see here. So next, let's look at that molar mass. Well, these are very different. Germane is pretty heavy, 76.6 grams per mole compared to methane at 16 grams per mole. That's really light. So the feature that likely varies the most between these compounds is going to be your molecular mass, your size. They're all very small circular molecules, even though I haven't shown you the molecular structure, so it's not going to be molecular shape. The biggest variation between them is size. So this is likely what's going to influence my intermolecular force strength. And with that in mind, well, I predict that the smallest molecule will have the weakest intermolecular force strength. And that means the lowest boiling point. And the largest will have the strongest and the highest boiling point. And sure enough, that's exactly what we see. Methane has a boiling point of negative 116 degrees Celsius. Silane was about negative 112 degrees Celsius, so a little bit higher boiling point ultimately because we're in the negative range. Okay, and germane at negative 88 is the highest of those boiling points. So as you are looking at different molecules and trying to predict which one has the highest boiling point or the lowest boiling point, or if you're looking at other liquid properties that you'll examine in the next few videos, consider these three different factors and try to figure out which one of these varies the most. Is it molecular polarity? Are the molecules very different in terms of the presence of electronegative atoms? Or is it the size of molecules? If the molecular polarity isn't a factor, this is likely the major factor influencing your intermolecular force strength. And if molecular polarity and size are roughly equivalent, then consider the shape of the molecules.